In our study of the Laplace transform, today I am going to introduce um, the step function. In fact, it is called unit step function. It is also called Heaviside step function. A unit step function is represented by u, and Heaviside step function uh, is defined as u0 t. It can be best understood graphically. So a ut is 0 up till t is equal to 0, and then it becomes 1, and this is the same thing, u0t. So basically this subscript is the time at which the step occurs. So if we shift this unit step function to some value c of time, then it is 0 up till c, and then it becomes 1 suddenly. This, in this notation, will be a shifted version of ut, and it will be written as ut minus c. But the Heaviside step function is written as uct. So this is just a matter of notation. I'm just telling you how it is represented in various texts. So basically, we will stick to this notation mostly, but if you encounter this notation somewhere, you should at least know what it is. So in a piecewise way, a unit step function at c is described as it is 0 up till c, but it is 1 after c and at c as well. So it jumps from 0 to 1 suddenly in no time, but at the jump location it is defined to be 1. If I have mentioned somewhere, let me see my previous notes whether I have mentioned this or not. Oh yes, in the lecture 11.2, the differential equation lecture 11.1, I have mentioned that it is not defined at t equal to 0, and that was not correct. Please correct it. So at the jump it is considered to be 1. So this is the correct piecewise description. Okay, so since we are reading about the Laplace transform, let us find the Laplace transform for this function. So the Laplace transform for u t minus c by definition would be solving this integral from 0 to infinity, multiplying e raised power minus st with the function that is being considered. Since it is 0 up till c, so basically this integral will be 0 up till c. So, and after c, the function becomes 1. So this is what we get. And this is equal to e raised to the power minus st over minus s, limits from c to infinity. So what do we get here is, because when we put infinity in here, it becomes 0, and c e raised to power minus cs. So we are going to get e raised to the power minus cs over s. So this is a transform pair, in fact. this is the Laplace transform of a unit step function that is shifted to the location C. So this is something to be remembered. Perhaps I have already told this. Yes, I think, yes, we found it in the previous lecture that the Laplace transform of ut is 1 over s. So combining these two results, can you see that if the function is shifted to the right or delayed by c, then the Laplace transform of that function is multiplied by e raised power minus cs. So you can find this for other functions as well, but let me write another functional transform for you, that if this is a transform pair, that some function ft has a Laplace transform of f of s, then if you remember, this ft is always multiplied by ut is understood because the function starts at t is equal to 0. So it's very important. So if this function is now shifted in time, so it becomes f of t minus some value t naught, not f of t. So f of t is shifted. So suppose this is f of t, some function, this is f of t, and we just shift it to some value t naught. So this becomes f of t minus t naught. There is a delay of t naught. The function starts after t naught delay, and the ut associated ut would also become ut minus t naught. Then the Laplace transform for this shifted version of this function will be e raised to the power minus t naught s into f of s. Now this is a very important result, and often we are going to make use of it. There is another use of the unit step function, that is sometimes some function, say force being applied to a body, is suddenly changed. So for example, let us say some function is defined in this fashion. It is some function f of f1 of t for t less than some value c, and then after c a new function is being applied. So when you write a function in this piecewise fashion, then if we have to find the Laplace transform, we are going to have to apply the basic definition, whereas we can use the unit step function to describe this in one line. So can you see that ft is equal to f1t? This is the function for all time, except that after c this function f1 of t is not there. So we can write it in this fashion. There may be other ways of writing it, but f2 of t comes after c, but f1 of t goes out after c, and we can multiply this thing by ut minus c. Now you can see before t is equal to c, this thing is 0. So this whole thing becomes 0, and ft is equal to f1 of t, which is the case here before t is equal to t less than c, before t is equal to c. And after c, this thing is 1. So f1 of t gets cancelled, and we are left with f2 of t. And you can see that this is an elegant description, a single straight expression for describing f of t. So any function that has a discontinuity in it, say say a function had this value, but suddenly it changes in value, so we have a discontinuity at this point 2. The value of the function before 2 was 1, and then after 2 it becomes 2. So how to write this? So by the way, it has a lot of similarity with the unit step function, the shifted unit step function ut minus 2. So can you see that ut minus 2 is actually shifted up? So by writing it this way, we can write it like this. So this function f of t is actually 1 before 2 and 2 after 2. So just in this fashion we can write it ft as 1 plus 2 minus 1 ut minus 2, or 1 plus 1 1 plus ut minus 2, which actually is what I was describing, that ut minus 2 has been shifted up by 1, is the same thing. So this unit step function is quite useful actually when writing piecewise functions, and we will make use of it. We are now going to introduce another very important, very important function that is used a lot in engineering, and it is one of the very interesting functions, although it's a mathematical concept. Let me see if I have covered it already in my notes. I think I would describe it. I think I did not describe it. Let me just verify it again. Okay, so that function is known as the unit impulse function. Again, it has another name, and it is also called the Dirac delta function. Dirac delta function. It is represented by this Greek letter delta. So delta t minus c would be described graphically as, up till this point c it is 0, after this point c it is also 0, but at c it is infinity. Now it is very difficult, very difficult to comprehend it, but instead of describing it like this, so we basically make this infinite value by an arrow. But if I tell you that the area under the curve of this function is taken to be 1, so the area under the curve is 1, it will be very difficult for you to comprehend it. So how it is defined is by a limiting function, or by using limits to a function that we can easily understand. So suppose we have a function which is some value um, in a short span of time. So suppose this distance is epsilon, So C minus epsilon is this point. This point is C plus epsilon. So what is the width of this pulse? The width is 2 epsilon, and if the height is now 1 over 2 epsilon, you can see the area of this rectangular pulse will be 2 epsilon into 1 over 2 epsilon, which is 1. So now if we describe this pulse using again the direct delta, the Heaviside step function or the unit step function. So we see this is a unit step function here in action, and there is another unit step function in action here. So basically when you go up, you use a positive unit step function. When you come down, you use a negative unit step function. So if there is a discontinuity with a positive rise, you use unit step function, you add a unit step function. But if there is a drop in the value, then you use a negative, you subtract the step function. So you can see, you can check for yourself that this can be written as a unit step function ut minus C minus epsilon minus, because this is positive, it goes up. When it comes down, you can write it as ut minus C plus epsilon. So this is this pulse. This is a pulse. A pulse is anything that occurs that is there for a short span of time. And if we now apply a limit, and you can see the area under the curve of this pulse is 1, and in the limit this epsilon tends to 0, the pulse width shrinks to 0, but the amplitude goes to infinity. And but the area you can very easily see, because the height, the value of this function in this period is dependent on the width, so therefore the amplitude goes up, but the area under the curve remains 1. So this is how it is described, and it is much more much easier to comprehend this unit impulse function or the direct delta function. Again, delta t would be at the origin. So let us try to find the Laplace transform. Okay, before finding the Laplace transform, there is a very important property of the impulse function. An impulse function physically is used to model a sudden application of a force. So for example, someone kicking the football, or someone kicking something or applying a force to something by a hammer. So the blow of a hammer is for a very short period of time, but a lot of energy is transferred at that time. So the property of that delta t is known as shifting property. I hope you get it by my description of it. Shifting, by the way, means that you shift something from something. So for example, when you filter something, filter is for liquids, but if the thing is not liquid or fluid, you use this word sifting. So for example, we sift the flour, atta, and try to remove the material that is not desired. So basically chanana is what sifting is. So let us say how this delta t can shift a function. So suppose there is a function f of t, some function, say this function, and it is multiplied by an impulse and integrated from 0 to infinity. Let us say this c is greater than 0 actually. So this is one of the powers of the unit impulse function or the impulse function or the direct delta function. This use is its greatest use, and you can see that it simplifies the integral. So what is going to happen? We know this integral from 0 to infinity passes through the point where this impulse exists, that is t is equal to c, and up till c this integrand is going to be 0 because this is 0, and after c it is 0. So basically the only point where this integrand will be non-zero will be at t is equal to c. So exactly at t is equal to c, f of t would be f of c, and because f of c is a value, so it will get outside of the integral, and whatever we are left with is an integral of the impulse. So we have just described that the area under the curve of the unit impulse function is 1. So basically this whole integral will be equal to 1, and what we are left with is the value of the function at the location of the impulse. Now this is a very useful property. You may not immediately recognize, but you can at least keep this in mind. So any function multiplied by an impulse and integrated over all the time is going to get you to the value of the function at the location of the impulse. So being a useful result, let me just enclose it for reference. So now we can, based on this property, it will be easier for us to understand how Laplace transform of an impulse at c can be computed. So by definition, this is going to be solving this integral from 0 to infinity, multiplication of e raised power minus st, which is actually some function, and then an impulse is being multiplied, and we are, by using this property, we are going to get the value of the function at the location of the impulse. So once again we can relate this result with this one. So if this f of t is an impulse, so the impulse, did I cover it? I just please wait for a moment. Let me see my notes again. Did I cover the impulse earlier? No, I did not cover the impulse. Okay, so I am writing it for the first time. So if this c is 0, actually we are going to get e raised power 0, and that is 1. So if the impulse is at 0, then the transform pair is this. So 1 is the Laplace transform of an impulse at t equal to 0. And now using this property, if this function is shifted to c, then its Laplace transform is going to be multiplied by the amount e raised power minus the amount of the shift s. So all these are useful results. Now this is these are two very important functions that are used in mathematics as well as in engineering, extensively used in engineering. So try to understand the concepts, underlying concepts. In the next lecture, we are going to see how this unit step function can be used to describe, say, a differential equation that has a discontinuous inhomogeneous term, and how the Laplace transform is going to help us solve that. It is of interest to both the ENS students as well as the differential equation students.